In the previous topic, we looked at the subject of acids and bases. This topic involves applications of aqueous equilibria, and one of those is the reaction of acids with bases. There are four combinations of mixing acids and bases, three of which I've included on this page. The first is to react a strong acid with an equivalent amount of strong base. Okay, the equilibrium constant for this reaction is 1 times 10 to the 14th, which is the reciprocal of Kw, since this is the reverse reaction for the autodissociation of water. So that was very easy to obtain. Okay, next we have an example of a weak acid strong base neutralization, and the equilibrium constant is still very large. It's 1.7 times 10 to the 9th. If we were to use a strong acid weak base, we would actually get a very similar number, say HCl and ammonia. So I haven't included that there. The fourth combination, which actually is not very useful in titrations, and that is to use a weak acid with a weak base. Okay, well, I've chosen two weak acids with very similar Ka values, formic acid, HCOOH, and HF. And if we were to try to do a neutralization with formic acid and fluoride, we would see that the equilibrium constant is 0.251, which means there'll be a lot of starting material left at equilibrium. Okay, this is how I derived at that number. This is the Ka for formic acid. This is the Ka for HF. And if I reverse the second reaction, then I would take the reciprocal of the Ka, and using Hess's law, if I add these two equations together, hydronium and water both cancel out, and then the resulting equilibrium constant would be the product of these two. So that's 0.251. Okay, so we don't typically do a titration involving a weak acid and a weak base. It's just not useful. Okay, if we react equivalent amounts, that is the same number of moles of a strong acid and a strong base, okay, such as HCl and NaOH, the net ionic equation is hydronium plus hydroxide gives 2 waters. Okay, and that's actually the net ionic equation for any strong acid, strong base, since the spectator ions will cancel out. And after neutralization, the pH will be 7. Sodium chloride is an example of a neutral salt. If we have a weak acid, strong base, and we react the same number of moles of weak acid and strong base, okay, at equilibrium, or at neutralization, I should say, we're going to be left with a weak base anion. Okay, which means that the pH is going to be greater than 7. It's going to be basic. All right, a third situation would be if we had a strong acid, weak base, and this is actually not correct. It should say it should say hydronium plus ammonia. And so after neutralization, we're going to be left with an acidic cation. So our pH will be less than 7. We're going to have an acid solution after neutralization. Okay, and then this was the one that's not useful. If we have a weak acid and weak base, okay, after neutralization, the pH is going to depend on whether the pKa of the acid or the pKb of the base is larger. Okay, the common ion effect really is just an example of Le Chatelet's principle. Okay, so if we start out with a system that's at equilibrium, and if we add a species to either the product or the reactant side, the system is going to shift in such a way as to consume whatever it was we added. And in this example, okay, if we have an acetic acid solution at 0.1 molar, its pH is 2.89. Okay, what if we take that same acetic acid solution and dissolve 0.1 moles of not only the acetic acid, but also the conjugate base, sodium acetate? Okay, so this time our base concentration is not 0, like it was in most of the cases in our previous chapter. Here it's going to be 0.1. Okay, we set up our ice chart the same way. And okay, our values at equilibrium, this will be what we're familiar with. This will be a little bit different since we didn't start out with 0. Okay, so we'll substitute these into our Ka expression, and we can approximate. We can assume that this X value in the numerator and in the denominator are both 0. And since we have equal molar concentrations of both the acid and its conjugate base, 0.1 and 0.1 divide out. And so X is simply equal to our Ka. And that's also equal to the hydronium ion. If we take minus the log of that, that will be 4.74. Okay, so why is there a difference in pH? Okay, because we added more of the product conjugate base, that suppressed the ionization of the acid. Okay, it shifted the system in the reverse direction. And this is merely an example of Le Chatelet's principle. Okay, so for 0.1 molar acetic acid solution, okay, as we add more of the conjugate base, we can see that the hydronium ion concentration is going to go down. Okay, so here we have the combination of acetic acid and sodium acetate in a 1-to-1 ratio. The pH is 4.74, and using the indicator methyl orange, the solution is yellow. Okay, the acetic acid by itself with a pH of 2.89 turns the indicator this purple color. All right, when we have a solution containing a strong acid and its conjugate base, a weak acid and its conjugate base, that produces what is called a buffer solution. And this only works with a weak acid. Okay, you cannot make a buffer, say, from HCl and sodium chloride. And these are just a few examples of buffer solutions. Okay, so a buffer is composed of a weak acid and its conjugate base. And one of the characteristics of a buffer is that it resists drastic changes to pH upon the addition of a strong acid or a strong base. Okay, and that's what this slide indicates. Okay, so say we have a buffer with equal concentrations of weak acid and its conjugate base. We add a small amount of OH. Okay, that's going to convert a little bit of weak acid into its conjugate base, but it's not going to change the pH very much. Okay, similarly, when we add strong acid, a small amount of strong acid to our buffer, okay, that changes the ratio a little bit, but the pH doesn't change very much. All right, this shows the effect of buffering. In a strong acid solution, there's no buffering. And so in order to get a pH of 4.74, we need to make a really dilute solution of HCl, 1.8 times 10 to the minus fifth. And this turns our indicator this red-purple color. Okay, if we take that solution and we add only a few drops of 0.1 molar sodium hydroxide, that's going to turn our solution yellow. There's going to be a large change in pH. Okay, if we take 0.1 molar acetic acid solution with a sodium acetate solution, okay, that's also 4.74, just like solution A. And if we add, again, 100 milliliters of 0.1 molar sodium hydroxide, that really doesn't change the pH very much. And so it won't change the color of the indicator. Okay, the Henderson-Hasselbalch equation is very useful in doing buffer calculations. It's sometimes called the buffer equation. This page is merely just a derivation of that. The end result down here is this pH equals pKa plus log of base over acid. Okay, if the concentrations of base and acid are equal, this ratio is 1. The log of 1 is The log of 1 is 0, and this term drops out. And at that point, the pH is equal to pKa. The most useful buffers are those in which this ratio of base to acid is close to 1. It doesn't have to be exactly 1, but if it's close to 1, then that makes a good buffer. If this ratio is, say, 1,000 to 1 or 1 to 1,000, that doesn't make a very good buffer. It doesn't do a very good job of resisting changes in pH. Buffers are extremely useful. They're extremely important, for example, in physiology. Your blood actually contains 3 different buffers. And the reason for that is that pH has to be carefully controlled. In fact, you can only tolerate a range of about 0.3 pH units. If the range gets outside of that, then you can die. Also, an environmental problem over the past several years has been that of acid rain and lake beds that have been composed of granite, which is calcium, which doesn't serve as a buffer. Those have been most affected by acid rain. Whereas those that have a limestone bed, limestone is calcium carbonate, which will produce a buffer solution. This will help the lake resist changes in pH. A titration is a procedure for determining the concentration of a solution by allowing a carefully measured volume to react with a standard solution of another substance whose concentration is known. Okay, and if we're doing an acid-base titration, the standard solution could be either the acid or the base. And then we react that with an unknown concentration of our either acid or base. We can use either an indicator or a pH meter to determine when neutralization occurs. All right, so where this is useful, and probably one of the most important things from this chapter, is that when we reach neutralization, the point of a titration is that when we reach the end point, the same number of moles of acid and base will have reacted. Right, here is an example of a strong acid, strong base titration, where we have the same concentrations of sodium hydroxide and hydrochloric acid. Okay, on the y-axis of this curve, we have the pH. On the x-axis, we have the milliliters of 0.1 molar sodium hydroxide that has been added. Where the curve has a vertical slope, where there is the largest change in pH, that is the equivalence point. And as we said near the beginning, when we have a strong acid and a strong base, at the equivalence point, the pH will be 7. Okay, so we have reacted exactly the same number of moles of acid and base when we reach the equivalence point. Okay, this continues to rise rapidly, and after the addition of additional sodium hydroxide, okay, you can see that the slope doesn't change much, but here it's just the concentration of the hydroxide that's going to dominate. Okay, so the equivalence point is the point at which stoichiometrically equivalent quantities of acid and base have been mixed together. In other words, the same number of moles of acid and base. Okay, so before we add any sodium hydroxide, we have only HCl. Okay, it's at a concentration of 0.1 molar, 10 to the minus 1. Minus the log of that, of course, is 1. And as we add sodium hydroxide, the pH changes slowly. And then when it reaches the equivalence point, there's a sudden increase. And then past the equivalence point, we have just excess OH. Right, so here is a table of sample calculations for pH in the titration of 40 milliliters of 0.1 molar HCl with 0.1 molar NaOH. And a useful equation is the concentration equals amount divided by volume. And if we use millimoles rather than moles, Molarity is moles per liter. Molarity is also millimoles per milliliter. We've divided both the, or I should say, we've divided both the numerator and denominator by 1,000, and so millimoles per milliliter is the same number as moles per liter. Okay, so at the beginning, we have 40 milliliters, and that's at 0.1 molar. So if we multiply these together, we get 4 millimoles. And, 4 millimoles divided by the total volume, which is 40 milliliters. Okay, that's 0.1 molar. And if we take minus the log of that, that's 1. Right, if we've added 10 milliliters of sodium hydroxide, okay, 10 times 0.1 is 1, so that's where we get the 1 millimolar. Okay, that will consume 1 millimole of HCl, and so we'll be left with 3 millimoles of HCl. So HCl is still in excess. So we'll take our amount, our millimoles, divided by our volume. Okay, now our volume is 50 because we started out with 40 and we added 10. And that gives us 6 times 10 to the minus second. Okay, 3 divided by 50. And if we take minus the log of that, that's 1.22. Okay, and then we can keep going. And then at the equivalence point, our pH will be 7. After the equivalence point, okay, all of the HCl will have been neutralized and we'll have just excess OH. Okay, so for example, let's take the second data point down here. Okay, after we've added 41 milliliters total of sodium hydroxide, okay, we're going to have 0.1 millimoles of hydroxide, and our total volume will be what we started with plus what we added. So our total volume now is going to be 81 milliliters. Right, if we take 0.1 divided by 81, okay, that gives us 1.2 times 10 to the minus third. And our hydronium would be Kw divided by that, or 8.3 times 10 to the minus 12th. And now our pH is 11.08. Okay, and you can see that with addition of more NaOH, okay, our pH continues to increase, but does so slowly.